Okay, we're
cool. I can? Cool. Hey everybody, how's it going? I have a little bit of a cold, so I don't sound quite as sexy as I normally do. I also am going to apologize to all the speakers after me who have to come and talk into this microphone. Sorry that you guys are all about to catch whatever it is I have, one of those things. So I'm going to talk about feature engineering today, but my talk is like a little bit short, so I have time to just basically pontificate for a few minutes, and I'm going to take advantage of that. I love this conference. This is like my favorite conference every single year. And I love it because it is just such a great mix of industry-oriented academic people, like people in academia who actually like care about industry and like care about real-world machine learning, and people in industry who have like a very strong academic background and can come give like serious, interesting, deep talks. I am not one of those people. My talks are mostly like fluff and pictures of cats, so I'm going to apologize for that. I feel sort of embarrassed to be here. But I loved Misha's, and I think, is it Eva or Iwa? What? Yeah, either one works. Okay, anyway, I love both of those talks so much because they resonated with my experience. Misha was talking about this sort of count-based machine learning algorithm and how it sort of evolved and kind of took over the ad industry. The first time I saw it was in 2007 when I started working at Google. And it was like, so I started working at Google. I finally am basically inside, Willy Wonka's chocolate factory, basically. And I am like Augustus Kloop, like rocking the wiki, just like, hoovering up as much information as I possibly can for like 3 or 4 days. I'm not even sure I slept, actually, for about 48 hours. And the very first thing I read was the details of how exactly Google's machine learning algorithm worked. It's called SmartAss. They've actually written papers about it and stuff like that, so I don't think any of the Googlers in the audience will like shoot me or stick a lawyer on me for talking about this. It was originally invented by a guy named Eric Veach. And Eric Veach is famous in kind of ad circles because he invented the generalized second price auction, which is also the auction that a lot of different ad companies, including Google, use for placing ads. Eric is like one of the scariest, like, smart people in the world. And I think he lives in Seattle, actually. He might actually be at this conference right now. Eric, are you here? No, he's got better things to do. Anyway, yeah, basically he was a graphics PhD. He did like computer graphics stuff. But Google needed a like proper real machine learning model. Like, people don't know this, but up until like 2004, Google's like machine learning model for like ad click prediction was just like number of clicks divided by number of impressions. That was it. That was the model. It was brilliant. Worked really, really well. So when Google wanted a sort of real, proper, defensible machine learning model, Eric basically, like, I swear to God, he got a book about machine learning and just like sat down and read it and came up with the count-based algorithm essentially himself. Like, and I was just like, wow, that's kind of like freakishly scary smart, right? That's sort of insane. Yeah, I don't know. It was kind of an interesting story. It was neat for me because I had not seen any of the previous papers in '97 or '91 or anything like that. I thought it was like the coolest thing ever. And just insanely, seriously impressive that this guy with no machine learning background whatsoever basically invented this thing himself. It was super cool. My other comment about Eva, you're just a great talk about experimentation and sort of planning for smart failure or planning for valuable failure. And I got a really kind of good lesson of that when I worked at Google. I remember I launched once a sort of bad experiment configuration. And I think I cost Google, it was something like $1.6 million or something like that in a span of about 4 hours or so. And the important thing, like when you work on these kinds of systems, is you kind of like gotta not care about the amount of money at stake when you make mistakes or when you succeed, right? Like all of Google's dashboards are very much like percentage based, right? There's no actual numbers on there because you don't really want to think, wow, I just lost $1.6 million. And I remember like Sridhar Ramaswamy, who was the VP of ads at the time and had to kind of clean up the mess that I made, was like, Josh, did you learn $1.6 million worth of information over the last 4 hours? Like something like that. Anyway, so yeah, anyway, great talks, guys. Thank you both so much. Those were just awesome. I loved it. If you don't know who I am a like internationally renowned, super famous data scientist. And like most super famous people, the thing I am famous for is maybe like kind of silly and embarrassing and stuff like that. And it's this tweet I did once, which is kind of a proper, defensible definition of a data scientist, someone who's better at statistics than any software engineer and better at software engineering than any statistician. This sucker will be on my tombstone. It's been retweeted like 1,000-something times now. So I have roughly like the same level of Twitter credibility as whatever Justin Bieber had for breakfast this morning. Anyway. So I like this definition a lot. It's nice, it's short, it's pithy, it works pretty well. And I swear to God, if I had a nickel for every time someone's replied to me and said something like, oh, does that mean they're worse than any software engineer or worse than any statistician? I mean, I would be retired at this point. I wouldn't have to go around and give talks anymore. And it's super annoying. But let me expand on the definition a little bit. Like, what does it mean for a statistician to not be like as good at writing software as a software engineer? I've worked with a lot of statisticians over the years at Google and other places, and there are a lot of statisticians who know how to write code. They can write R code, they can write SAS code, some of them can write Python, some of them can even write C. But they don't really write like good code. They don't really write like tests. They don't really write like even functions sometimes are kind of a little bit scarce in statistician scripts. They don't really care about like robustness. They don't really care about creating things that are designed to be used by other people the way that software engineers do, the way that it means to be kind of part of a software engineering team. So if you don't write unit tests, if you don't write functions, if the code you write is just for you, it's not for other people, you are not, by my definition, a data scientist. Flip side, a lot of software engineers in the world who you can like give them a data set and give them like a function that computes like a logistic regression model, and they can like, they know how to call a function if they're software engineers. They can pass the data into the function and get a result back. But in my experience, software engineers don't typically know like how to interpret the results of doing regression models. The other thing, if I had a nickel for every software engineer who's fit a regression model on a set of observations that were not independent of each other, I would also be retired by now. I love that joke because like there's the few statisticians in the room who like laugh and nod like quietly because they've been there too. Yeah. If you don't actually understand the assumptions behind statistical models so that you know how to correctly interpret the outputs, you are not, in my definition, a data scientist. All right. Now, Eva was talking about data scientists at work. Like, what does a data scientist do all day? And mostly what we do is we cleanse and prepare data. That's really, at the end of the day, that is what like data science, all this fancy New York Times, super great, exciting field is really about. We are data janitors more than we are data scientists. And I guess I want to kind of come out and confess, and I know that it's really important for a lot of reasons, but this is us, right? This is just inside the family. I really enjoy data cleansing and feature preparation. I want to come out and say it. I really like it. I really like it a lot. It is, I swear to God, it is like a Zen, like Buddhism meditation kind of thing for me. I was interviewing a couple of years ago at Dropbox, and Dropbox, yeah, I interview places. It happens. It's okay, right? I'm coming up on 4 years at Cloudera, so kind of my big vesting date is June 11th at noon roughly. So anyone wants to hire me, like now is the time. Anyway, Dropbox does this great interview process where, and I'd never done this before. I thought it was super cool. Where they bring people in and they just give them a data set and a problem. And they're like, here's this data set, here's this problem. You have 2 hours to use whatever tools you like, and you can just like sit here and analyze this data and just tell us, at the end of it, like what you found interesting, like create a presentation, give a talk about it. And I swear to God, it was like the happiest 2 hours of like the last 4 years of my life. I was like left alone. There was no email. There was no one asking me questions. There was no one asking me to give talks. I could just sit there and analyze data. Like I didn't even like feel my ass in the chair. You know what I mean? It was like I was just so insanely happy. I love data cleansing. I love data preparation. I love the work that we do, and that's good because we have to do it a lot, right? And I think I feel very lucky. I think like the key to success in your career is to find something that other people find really boring and awful and tedious that you don't like mind so much. Like that is sort of the key to making money in life, because people will pay you lots of money. This is a picture of me at my house in San Francisco. People will pay you lots of money in order to do things they consider tedious and awful and unfun. And if you like doing those kind of things, you guys know Craig Newmark, right? The Craigslist guy. So Craig is like very, very introverted, right? He's like sort of somewhere on the autism spectrum. And Craig, his title at Craigslist, I think to this day, is Chief Customer Service Representative. Because Craig is like insanely good at sitting there and like just answering emails, just like customer service emails, like down the list. He is freakishly insanely good at it, a job that most of us would find like tedious beyond comprehension. And that was what made Craigslist succeed initially. He created this community by just being super awesome at mowing down customer service emails. That's like what he does. He does it really, really well. So kind of a pro tip, right? If you can find the thing that you think is either interesting, ideally interesting, or at least like tolerable, that other people think is just unspeakably awful, that is your career. That is the way to make lots and lots of money. So look for that. So anyway, this whole sort of thing has been feature engineering, data cleansing. It's been great for data scientists. And we've done like some pretty cool, interesting things. Like we as a data science community, right? We sort of created Watson. And Watson was really nothing more than just a ton of very tedious, awful, feature engineering processes, like feature engineering tasks, right? Building these models that could beat, Ken Jennings and the Brad guy and all those other super smart people, right? So we've accomplished some kind of incredible things with our feature engineering over the past, 5 years or so. So this is like, I feel like, right now this is sort of like a fantastic golden age for data scientists, for people who find data cleansing like intrinsically satisfying. But I also think there are like possibly some clouds on the horizon. And the biggest cloud I want to talk about, this is the elephant in the room, is deep learning, right? Deep learning. I think anyone who's like me, who really like enjoys being left alone in a room to just sit around and analyze data and just create features and see how well they work, is kind of terrified by the prospect of deep learning. Because deep learning, as far as like, what little I understand of it, means that we don't really need to do feature engineering anymore. The computers are going to do feature engineering for us. And our job is going to be to tune like 4 billion parameters or something like that no one really understands or comprehends in order for the machine to do a better job of doing feature engineering. And I mean, we got to be kind of careful here, everybody. Like if it gets out, like outside of our little community here, that no one understands how any of these things work, we're in trouble, right? Because like we're very replaceable at that point by monkeys that can also just do like parameter tuning, right? You don't need a PhD to sit there and just like invent parameters and run models. I'm pretty sure, okay? We were really lucky around bootstrapping, right? We kept bootstrapping a really good secret for the last 35 years. That's awesome. But I mean, I'm worried about this, okay? This is like a real thing. So I mean, for a lot of machine learning problems, in particular like image classification tasks, like figuring out pictures of cats on the internet, the deep learning models are just so much better than anything human generated that no one really cares about the fact that we don't understand why they work. Like we don't understand how our parietal cortex really works either, but we can still see. So if we're solving the problems, like no one really gives a damn that we don't understand how these things work. So my concern and sort of like my question as I see deep learning models kind of expanding from these like visual classification tasks to things like speech and things like text and sort of other areas of machine learning, my question is basically like, are we still going to be necessary? Is like feature engineering, domain expertise, is this stuff still going to be useful in a world where we have deep learning for all these different kind of things? And it's early stages on all of this other stuff. It's early stages on text sort of based deep learning models. They don't work super well yet. Speech stuff looks a little bit better, at least for certain tasks. But we're still not to the point there where we're really doing like super amazing, ridiculously awesome stuff like we are with visual classification tasks. And so I was kind of like thinking about this, and I was trying to understand like why, like what exactly is it we're doing, like philosophically speaking, roughly. I realize how pretentious that sounds. I apologize. What is it we're doing when we're doing feature engineering? And the answer I came up with was that we are providing context to the algorithm that is not available in the data. And I haven't quite figured out how to explain this yet, so kind of bear with me. When I basically have a deep learning model and I have a picture and I have a label associated with it, right? This is a picture, this is a cat, like the label is cat. Roughly speaking, all of the information that is available to solve the machine learning problem is available in the data. There is no like extra information, no real extra context that the algorithm needs in order to like find the features required to solve the problem. Now, when I'm fitting like a classification model to predict like credit risk or something along those lines, right? There is actually additional context that I know as a data scientist about the problem I'm trying to solve that isn't necessarily in the data. The data is sort of like, for a lot of problems, it's kind of like an archaeological record, right? And we are trying to basically put some meat on those bones. So for instance, if I'm doing like a credit risk scoring model, I know that certain things kind of matter for people like paying off their debt on time versus not. And I know that like the sort of difference in income, like the sort of effect of the income variable, will probably be logarithmic because of like, marginal utility and stuff like that, right? I know extra stuff about the problem I'm trying to solve that isn't in the data. And when I'm doing feature engineering, I'm trying to find kind of proxies for my additional context, my additional knowledge, and sort of find a way to represent that additional context in the data in order to build a better model. Deep learning works really, really well when there isn't actually any additional context, when everything you need to know is in the data. There's no additional information I can provide above and beyond the data that will help the model do better. And when there is that additional context, I think it's harder to do deep learning models well. Or at least we're going to need a lot more data than we have now, and that data is going to need to capture a lot more of the context around problems than it has before. So that's my sort of optimistic outlook on like our futures. I think we have a sort of future doing fun, interesting, Zen-like feature engineering, data cleansing stuff, so long as all of the context, all of the data in the world is not fundamentally digitized, and is not digitized is like such an East Coast word, is not available to the algorithms, is not available to the machines. As long as there is context that is sort of in the ether, we will be useful. Of course, the amount of context in the ether is like going down like all the time, right? We're recording more and more and more of the stuff. So like, as someone who does feature engineering, as someone who enjoys doing feature engineering, at least when I get a chance to do it, I'm interested in ways we can do it better. I'm interested in ways we can do it more productively. And I'm interested in sort of systems for human-machine collaboration, where I can offload some of the more tedious aspects of the problem to the machine, but not necessarily kind of remove myself from the process entirely. Now, the paper I kind of recommend y'all read on this subject is called Brainwash, and it's by Mike Caffarella and Chris Rhee. They wrote it a few years ago, back when Mike was still at Michigan and Chris was at Wisconsin. I think they're both at Stanford now, because the sort of inexorable pull of Silicon Valley just brought them over from the Midwest. But Brainwash was really about building an IDE for feature engineering problems. All right, like creating an IDE that is customized for the problems of saying, hey, we have a whole bunch of data. It's got a fairly complicated structure associated with it, so we're going to need a fairly flexible data model. The data model they ended up coming up with to represent events or objects in the system is basically like protocol buffers, more or less. Essentially, it's a protocol buffer. We have tuples, we have lists of tuples, we have records. That's sort of the core of the idea. I can create features. I can write code that basically computes new features off of this data, and then the system will automatically go and compute summary statistics. It will automatically go and find extremal observations for me. It'll go find what's the min for this feature, what's the max for this feature, what's the observation that generated that. And then it will actively like sort of pick up new features as I create them and try to integrate them into existing machine learning models that I'm building to see if those features actually improve my model in some substantial way. So it's a sort of much more like kind of interactive IDE style process, as opposed to the kind of discrete tasks of like write the code, test the code, see that it fails, fix the code, run it on all the data, find the other observation that it fails on, find the value where like the output of the feature is basically meaningless, all that kind of like nonsense, tedious stuff they're roughly trying to do away with. For me, this was an interesting paper because it sort of dovetailed nicely with a problem that I've been interested in for about a year now. And I call it like the operational analytical impedance mismatch. And the core idea is that we work with data very differently in operational online systems than we do in offline analytical systems. And the sort of simplest example of this is like, say, a third normal form, kind of nicely normalized relational database schema versus a star schema, right? Because in the online operational world, we're usually operating on like one record at a time, one user at a time, one event at a time, that kind of thing. Whereas in the analytical world, when we're doing summary statistics and we're fitting models, we're processing hundreds, thousands, millions of records at a time. We're much more oriented towards kind of batch computation, batch model fitting, all that good stuff. So whenever we kind of want to go back and forth between these two different worlds, there's always this annoying step where we have to translate the code we wrote against the analytical data model into a form that can work against the operational data model. So I build a model over here, I've got a whole bunch of feature engineering code I have to find against one data model, and now I need to go rewrite all of that code to work against a completely different data model before I can deploy this model to production. And I think this sucks. And I think that this is actually not necessary anymore. I don't think we need to actually have a different data model for online and offline serving, offline analytics, offline model building, and online model serving. So the data model I've come up with, I've been sort of nicknaming a Supernova Schema. And I call it a Supernova Schema because it kind of looks like a star schema where some of the like fact tables have kind of collapsed into one of the dimensions. Okay? Technically speaking, like I had an astronomer kind of approach me about this. Technically speaking, that should be called a black hole schema. But I don't think the marketing of black hole schema would work quite as well for like roughly what I'm going for. So we're going with Supernova Schema for now. The idea is we create a record for every entity in our system. Every user, every car, every oil well, whatever kind of system it is we're trying to do machine learning on. And inside of that, we have a bunch of like sort of static attributes of that entity. And then we have a bunch of arrays of records that represent events about that entity. This person, logged into our website. This person called into our call center. This person made a purchase. All these different things are inside sort of different little arrays of structs. In the picture here, the price field there at the bottom, the price field is an array of structs. Each one is sort of a type and then an associated price associated with it. Now, if you are used to working in operational contexts, this data model will look insanely, embarrassingly familiar to you, right? This is the Twitter API. This is MongoDB. This is HBase. This is Cassandra. This is, like, roughly speaking, what rows, records in these sort of NoSQL stores and APIs look like. The question then becomes, how do I make this sort of crazy, complicated data model accessible to people who are used to working in R and Python and SQL? How do I make it easy for them to work with these kind of things at scale to define new features, create new metrics? And the trick I came up with is to recognize that these arrays of structs, these nested arrays of structs, look like tiny little data frames or tiny little SQL tables. That's roughly what they look like. You have an itty-bitty SQL table inside of each record. And so what each record basically looks like is a database, right? It's a database for this user with all these different tables inside of it. And so I created a project called Exhibit, which basically allows you to execute SQL code inside of each record and then aggregate the results of those SQL queries across all the different records in the system, right? So, yo dog, I heard you like SQL. I put SQL in your SQL, so now you can query while you query, right? Now, I use Exhibit for a lot of different things. I'm using it right now for ETL-ish projects at my customers, right? I have a customer who wants to compute something like 2,500 different metrics for each of their user accounts. And we can do this much, much more efficiently at scale if we write sort of a small series of MapReduce jobs. One series that is designed to build these kind of complex nested superstructures, and then a follow-up job which basically goes and computes all 2,500 metrics in a single pass over this sort of giant denormalized data than we would if we wrote like 100 different MapReduce jobs or 100 different queries that had to reprocess the same data again and again and again and again in order to generate exactly the same answer. But I also want to use Exhibit as actually like a foundation for a sort of feature engineering, Brainwash style ETL IDE tool, roughly speaking. And so I actually built something that kind of works. And I should say this is all like open source. I'm developing this all in the open. The code I'm about to run for you, you can run yourself and all that good stuff. So what I did here, this is a demo, so it'll just totally go awesomely well. I basically got a bunch of football player data from a website called armchairanalysis.com. And basically Armchair Analysis allows you to download like 15 years worth of NFL data. So for like every player, every play, every single event, every game in the NFL, I created a Supernova record for every player, okay? So every player has a sort of static list of attributes over here, like what's their first name, their last name, what position do they play. And then for every single play that involves that player in any way, every pass play, every rush play, every two-point conversion, and every field goal, I have an array of structs that I can visualize here. You guys can totally feel free to make fun of my JavaScript skills. Like this is like a week's worth of JavaScript for me to like learn how to do this, which to be honest with you was actually surprisingly satisfying. It was like the feeling of remembering like what it was like to be an engineer like early on and not really totally know what you were doing and have to like kind of figure stuff out. It was actually sort of super fun. So if anyone would like to hire me to become a JavaScript developer, that would be awesome. Anyway, June 12th. Yeah, it's like real. I mean, I don't know. I think the rush is going to be pretty intense. So June 11th at 12:01 p.m. is probably your best bet. All right. So, kind of cool. I've linked all these records together. So, for instance, I can call up like the Tom Brady record, which is super enormous because Tom Brady's in basically every play in the NFL for the last 800 years. But anyway, every single player has a record all linked together. And then down here, what I can do is actually like experiment with running SQL inside of SQL. I can execute SQL code against just the data on the page, right? I can look at sort of like various results, you know, so when it's like from passes, and I'm not super great at SQL, but that's all right. Group by def, run this locally, sort of see the results over here, interact with these. And I can also like save these kind of computations away and then restore like other sort of metrics, other computations I've done. So for instance, if I want to find the number of rush yards per game for Tom, which is very, very small, I can easily like call up not only the value of that metric, but the code that was used to generate it, right? Like the actual SQL code I used to write against this kind of thing. So my dream, my goal is to get to the point where you can sort of be interactively creating new metrics, creating new features off of the data you see on the page. We can take the code you write to do this and then basically like export it, scale it up, run it on like a small test set of records locally inside of a server so we can verify that it works for extremal records. We can give you quick feedback on how well the metric performs. And then we can take the features and push them out to basically either like the Uyala Spark job server or maybe a big MapReduce job or whatever, which will go compute a whole bunch of summary statistics, compute information about these features, and report it back to us. So basically, we're just interactively sitting here exploring data sets, looking at records, creating features in real time, and then all in the background, all the kind of eval processes continually going on. And ideally, we would get so smart at this that we could actually like, you know, have the machine learning algorithms themselves like basically write code that would evaluate different combinations of features, that would detect when there were parts of the data set we weren't really using that well. All that good stuff would basically become possible. So I'm working on this. I'm not super great at JavaScript yet. I need a lot of help. It's up on jwills at /exhibit up on GitHub. Thank you all. Thank you very, very much. I appreciate it. Thank you, man. Do I just plug it in next? Okay, I'm not sure.
Okay, you got it? So